when we talked about the possibility of interstellar travel and the possibility of alien civilization spreading around the galaxy, we addressed the issue that stars are just really far apart, that even if there are a million civilizations in our galaxy, that's only one out of every 100,000 stars, which means the closest inhabited star system to us could be hundreds or thousands of light years away. This does not bode well for the prospect of traveling from one star system to another. So what we want to talk about instead is the possibility of actually communicating more indirectly across interstellar distances with alien life forms, alien civilizations that may exist elsewhere in our galaxy. We mentioned the very limited attempts we've made so far of sending spacecraft into interstellar space. We talked about the Voyager record and the Pioneer plaque. So we have thrown sort of messages in a bottle into interstellar space, but it will take these messages tens of thousands, hundreds of thousands, millions of years to get to any other planetary systems. So while these were interesting experiments in figuring out what would we put in a message to an alien civilization, they weren't really serious attempts to communicate with an alien civilization. They were more a proof of concept. We want to talk about something more concrete. How would we actually communicate with an interstellar civilization, with an alien technological civilization far from the Earth? Is it even possible to imagine? The problem is that they would be far away from us, so whatever signal we send has to be able to travel tens of thousands of light years, hundreds of thousands of light years through interstellar space. What kinds of signals are possible to send? Well, we've got the whole electromagnetic spectrum. We could send ultraviolet, infrared, X-ray, gamma ray, whatever, some kind of broadcast signal out into space. Which should we choose? Well, we know from talking about what kind of observatories we can build on the Earth that not all electromagnetic radiation makes it through our atmosphere. That the only light that makes it through the atmosphere is visible light and radio waves. Those are the only kinds of telescopes we can build on the ground. If we're sending a signal to some kind of alien planet that we don't know anything about, we want to make it as likely as possible that they get the signal. So we want to send it using some kind of signal that will make it through their atmosphere, whatever it is, to the ground, which means visible light or radio. Visible light may be not a good choice. We can imagine a planet like Venus or like Titan, where barely any visible light gets through the atmosphere at all. Radio waves, probably a better choice. Radio is probably also a better choice because radio telescopes are easy and cheap to build compared to visible light telescopes. Radio transmitters are easier to build than shooting a powerful laser into space that has to outshine the sun. And because things like stars are fairly dim in the radio, in other words, we don't have to compete with the visible light of everything else in the galaxy if we want our radio signal to be noticed. If we wanted to send a visible light signal to an alien planet by just blinking a laser out into space, that laser would have to be brighter than the sun in order for them to see it. Well, that's a tall order technologically. The sun is actually very dim in radio. This is, by the way, the biggest radio telescope ever built so far by humans, the Arecibo radio telescope in Puerto Rico. It was destroyed by a hurricane a few years ago and no longer exists. I think a bigger one is being built right now in China. We can build huge radio telescopes at very little expense relative to visible light telescopes. And as I said just a second ago, and we look at the sky with a radio telescope, it looks like this in the daytime because the sun doesn't give off many radio waves, and those radio waves are not scattered by the atmosphere the way visible light is. Radio astronomers can work 24/7. They can do radio astronomy in the daytime just as easily as they can do radio astronomy in the night, and the only thing that disturbs their signals is things that give off radio waves. This bubble of gas looks like a former supernova remnant, something like that. That looks like a galaxy. So there's less competition, if you want to think about it that way. If you want to send a radio signal into the sky, there are fewer things that you have to outshine in order for your radio signal to be noticed. So most astronomers who think about this subject, and it's not many of them, but astronomers who think about communicating with extraterrestrial civilizations consider radio waves the obvious choice. Our biggest radio telescope, which until very recently was Arecibo, could communicate with an identical telescope all the way on the other side of the galaxy. Radio waves require very little energy. They are scattered very little by interstellar stuff. So a radio signal that was powerful enough could be detected with our current technology all the way across the galaxy. Another reason why astronomers think that radio signals are the best choice for doing this. What frequency should we use to either broadcast or listen to a radio signal? Radio signals have different frequencies, right? We can use a radio signal to send information, but we have to know what frequency to listen to. If you've still got an FM radio in your car, you probably have one but don't use it, but when you turn the dial on that FM radio, it selects different frequencies, 101.3, 101.5, 101.7. How would we know what radio frequency to send our signal to the aliens with? Or how would the aliens know what radio frequency to send their signal to us? We don't know. We could just send it on a bunch of frequencies and hope they notice. Or we could try to pick a frequency that we think they're probably already looking at. And this is one idea that has to do with a particular frequency of radio waves that's emitted by very cold hydrogen gas in interstellar space. When we talked about atoms emitting light, we talked about electrons jumping from one energy level to another. This is not that. This is much less energy than that. This is the energy that is given off when the magnetic field of two electrons. Okay, so electrons are they're spinning, so they're like little magnets. So the nucleus of the atom is like a little magnet, and the electron is like a little magnet. And those magnetic fields can either be lined up, or they can be in opposite directions. And this has more energy than this. Think about just getting two magnets with a North Pole and a South Pole and sticking them in a drawer with their North Poles and South Poles lined up. If you get them close together, they will want to flip. Okay, the North Poles repel the North Poles and the South Poles repel the South Poles, and they will flip over because that's a lower energy configuration. The same thing happens to the spins of a nucleus and an electron. They can go from being lined up to being anti-lined up. And that process gives off a little bit of energy. And that wavelength of that radio wave given off by that process has a wavelength of 21 centimeters. What does that mean? That means if you are looking for the cold hydrogen gas between the stars, what you look for is 21 centimeter radio waves, because that's the kind of radio waves that these things give off. Well, if the aliens have astronomers who are exploring the galaxy, trying to map the galaxy, trying to figure out where all the hydrogen gas is, they will build a radio telescope and they will look for 21 centimeter radio waves. And if we want them to notice us by saying, hey guys, we're over here, we're an alien civilization with radios, we could send a signal with that same wavelength and it would be detected. Or vice versa. If the aliens know that out there's probably some primitive planet where guys are just figuring out radio astronomy, that's us. Let's send the signal on 21 centimeters so they will stumble upon it while doing regular old radio astronomy. This involves trying to guess at the motivations of aliens, which is a tricky thing to try to do, but we don't really have any choice. So things like this are the kinds of thought processes that scientists go through when figuring out how do we imagine sending one of these signals? How do we imagine how to send a signal that will be noticed and will be detected? This is a map of the galaxy in 21 centimeter radio waves, showing the material and the disk of our galaxy, the dust and gas between the stars. And so the fact that we made this map in the process of mapping the galaxy means we are all the time looking at 21 centimeter radio waves, and we assume that aliens will be as well. Another question when we're talking about now, at this point in the 21st century, communicating with imaginary alien civilizations. What should we do? Should we send a signal out into space, or should we listen for a signal from space? We've done both. The signal we sent was very simple and very primitive, and I won't go into the details of it right now. It was more of a proof of concept back in the 60s. But the argument goes like this. Look, if there are aliens, they are probably more advanced than us. Well, if there's an alien civilization, it's got to be more advanced than us, because it couldn't be much less advanced than us, because we've only had radio for like 100 years. So it doesn't make any sense, really, to send a signal when the huge probability is that the civilizations out there are more advanced than us and have been doing this for millions of years. We should listen for that signal by just pointing our radio telescopes up and seeing if we get a signal. That process, the search for extraterrestrial intelligence, is called SETI, and we've been doing it for a long time. We've been doing it since the 1960s. The problem is it produces a lot of data. We've got to listen to all of space at a bunch of different frequencies all the time and look for a signal. One of the first examples of a distributed computing project. Distributed computing is when you have a bunch of computers working on a project at the same time. One of the first examples was something called SETI at Home back in the late 1990s, early 2000s. And SETI at Home is a program you could download on your computer. It was basically a screensaver. People don't really use screensavers anymore, but the idea was that when your computer isn't doing anything, a little screensaver comes up with toasters on it or whatever, and it keeps the image from burning onto your screen. Screen burn-in is not a problem anymore with LCD monitors, but back in the day of CRT monitors, if you kept an image on your screen for too long, it would get burned into the phosphors of the screen. So they had screensavers. SETI at Home is a screensaver that, instead of just showing flying toasters or swirling colors, would download a piece of data from the Arecibo radio telescope and would analyze it looking for signals, looking for something that stood out from the background. And when it finished analyzing that data, it would send it back to Arecibo and it would download another piece of data. And over the process of this, however long, I installed SETI at Home on all the computers at my school where I used to work back in 2001. In the process, the project, by running on hundreds of thousands of computers all at once, analyzed the equivalent of hundreds of years of what it would take in one computer to do. So by having hundreds of thousands of computers do this project, it analyzed hundreds of years worth of data, so that NASA's computers didn't have to work for 100 years to analyze the data. Did they find any alien signals? No, they did not find any alien signals. What were they actually looking for? What are you looking for when you look at this data? You're looking for, so they separate the data into, this is frequency this way, time this way. They're looking for a spike. You're looking for somewhere in the signal of just static noise. What is this signal? Imagine just taking an FM radio and tuning it between stations. You just hear noise. But if you hear some kind of signal that stands out from that noise, that's an indication of, oh, maybe there is something here that is artificial, not just static. An actual signal, what would aliens send to us? What would a signal look like? It would be a series of data points, a series of beeps that could be reconstructed into something meaningful. How do you say something meaningful to an alien civilization you know nothing about? One idea is you send a mathematical pattern that they will recognize. So imagine, instead of just sending a bunch of beeps, you sent something like beep, 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 beep. So one beep, then a rest, then two beeps, then a rest, then three beeps, then a rest. We would recognize that as a pattern. 2, 3, 5, 7. What are those numbers? They are odd numbers? No, they're not. 2's not an odd number. What are these numbers? They're prime numbers. 2, 1, 2, 3, 5, 7. And then we'd wait and say, what's the next one? Should the next one be 9? No, the next one should be 11, and then 13, and then 17, and then 19. We would recognize this as an artificial signal. There's no way that some pulsar or some colliding neutron stars could beep out prime numbers. So if we saw a signal like this, we would recognize it as something artificial. We would recognize it as the product of some kind of intelligence. We could also use a radio signal to send binary ones and zeros, either with a long beep and a short beep, like Morse code, or a low beep and a high beep. And in other words, a quiet, loud, quiet, loud, quiet, loud, or long, short, long, short. Any two signals that are distinguished from one another could be sent to encode ones and zeros. And if you know anything about computers, you know that all the data on all the computers everywhere in the world is encoded in binary. It's encoded as sequences of ones and zeros. So we could send binary data into space, or we could receive binary data from space encoded in a radio wave. But what about the information in that? How would we send information? If we think about the binary that we use in computers, there are certain rules that we have built into the computer for decoding certain binary sequences of ones and zeros. For example, one is called ASCII, A-S-C-I-I. ASCII associates certain binary digits with certain letters. So when you send a text message, what you're sending is a series of ones and zeros, but the person on the other end has a device that understands what ASCII is and can convert those ones and zeros back into a sequence of letters. When you open a JPEG or a GIF or a PDF, what that suffix at the end of that file tells the computer is what rule to use for decoding the ones and zeros. JPEGs and GIFs and HEICs and the PNGs, all these different image formats are different rules for converting ones and zeros into pictures and colors or sounds. MP3 versus WAV versus MOV versus AVI. Every one of these file formats has hiding behind it a set of rules for turning binary into something else, a picture, a sound, a movie. How could we send a picture to the aliens if they don't know the file extension, if they don't know the rule for turning those ones and zeros into something else? We would have to help them, or vice versa. They would have to help us. If we detected a big block of ones and zeros from space, how would we know what to do with it? Here's one way that we could have a clue. Suppose we got a big long sequence of beeps and boops, longs and shorts, highs and lows, ones and zeros. How do we know what this says? Well, suppose it was sent in a block of 144, and then it stopped, and then there was another 144, and then it stopped, and there was another 144. We would say, aha, number 144 must be important, because all the blocks are 144. Well, what's special about 144 as a number? 144 is a perfect square. It's 12 times 12. Let's put these ones and zeros in a 12 by 12 array. When I put these ones and zeros in a 12 by 12 array, I suddenly see structure. I suddenly see a pattern. If you squint and look at your screen, you might be able to see it already. If I say, well, this looks like a picture, I'll color the ones one color and I'll color the zeros another color. I get something like this. Okay. Or if I color them a little more bold, I get something like that. So I have sent a picture, a very simple picture, in a block of ones and zeros with a codec, a rule for decoding the data kind of built into the structure. Now you can't do much with 144 bits, but if it was not 12 square, but 1,000 by 1,000, or a million by a million. I could send much more information. I could send images, I could send sounds, I could send video. If I made the rule for decoding that data obvious. And again, we're thinking about how to make something obvious to an alien civilization who shares nothing with us, doesn't share any languages, doesn't share any history or any common experience with us. What are the only things that an alien technological civilization would share with ours? Well, mathematics. Okay, the rules of mathematics are the same everywhere in the universe. Anywhere in the universe, if you take the circumference of a circle and you divide by the diameter of a circle, you get pi, 3.1415, whatever. So mathematics is universal. We can frame our message in the language of mathematics, or the aliens would frame their language or their message in the language of mathematics. Physics and chemistry are universal. The periodic table of elements is the same everywhere in the universe. Now, this particular arrangement is idiosyncratic to humans, but the fact that carbon has a molecular weight of 12 and nitrogen 14 and oxygen 16, that's the same everywhere in the universe. The properties of a black body spectrum are the same everywhere in the universe. Any alien civilization which has studied stars will recognize the HR diagram. Again, they might not use graphs the same way we do, but the relationship between, say, the mass of a star and the luminosity of a star would be understood by any alien civilization. If we sent aliens the mass of our sun, how would you send the mass of our sun? You would send it in the multiple of hydrogens. Our sun has 10 to the whatever hydrogen atoms in it, and so that's what its weight is. If we sent aliens the mass of our sun, they would immediately know its brightness and its luminosity from the HR diagram. If we sent a picture of the sun's black body spectrum to aliens, they would immediately know the temperature of our sun. And vice versa. If the aliens sent us an HR diagram with a dot on it showing their sun, we would know a huge amount about their planetary system already, just by knowing that their star is an M-type star with a surface temperature of 3,500 degrees or whatever. It is possible to imagine communicating in the language of science and math a great deal of information to a hypothetical alien civilization, and it's possible to imagine an alien civilization communicating a great deal of information to us. Will it ever happen? Probably not. Maybe not. Am I an optimist or a pessimist when it comes to questions like this? I'm an optimist with respect to extraterrestrial life in general. I'm even an optimist when it comes to advanced extraterrestrial life. I think there are other, or have been, other civilizations in the galaxy like ours, maybe more advanced than ours. Do I think that they last for millions of years so that we would detect them and know about them? Which they would have to in order for us to overlap? I don't know. I'm not as confident about that. But there's no way to know the answer to that question but to listen. So we devote a small amount of time on our radio telescopes to pointing them up into the universe and listening for radio signals. Even if we never detect anything, that tells us something. It tells us something about what kind of population the galaxy has. If we listen to the sky for 1,000 years and hear nothing, that tells us that the galaxy is pretty empty. By the way, these signals don't have to be intentional. Every radio transmission that Earth has ever generated is leaking out into space. Every TV show from the 50s and 60s, every radio broadcast is going out into space. It's very unlikely that aliens will be able to decode those because they don't know the rule for turning, for example, a black and white TV transmission from 1962, the rule for turning that into a movie. Maybe they're smarter than us. Maybe they could figure it out. Maybe they could try a bunch of things until suddenly a picture of I Love Lucy appeared on the screen. Maybe not. It's hard to say. Likewise, any alien civilizations using radio technology, even for a little while in the past, those radio signals would be leaking out into space and we could detect them as well. So we might just accidentally find a radio signal, an obviously constructed, obviously artificial radio signal from an alien civilization, which even if we couldn't decode it, would tell us a lot about the universe that we live in. So, do I think we should devote billions of dollars to SETI? No. Do I think we should devote a couple $1 million to SETI and just keep our ears open and analyze all that leftover data for signals? Sure, why not? It's a small investment in what would be a discovery that changed the course of human history.